Hi students, myself is Vedamurthy. Welcome to my channel. So today let us continue with the chapter 4, unit 4 of class 11 and as per NCERT as well as PUC class. Unit 4 is the chapter belongs to chemical bonding and molecular structure. I have completed already 3 videos. If you want interest to see those videos, please check in the description. You'll get the videos and please watch all these videos. So bond parameters. What are the bond parameters? The bond parameters are bond length, bond angle, bond order, bond enthalpy, resonance structures, okay, and bond polarity or polarity of bonds. These are the points are coming across in the bond parameters heading. So today we'll cover out of 5 we'll going to be cover a 4. First, number 1 is bond length. Bond length usually is defined as the equilibrium distance between the nuclei of the two bonded atoms in a molecule. Bond length is described as the equilibrium distance between the nuclei of the two bonded atoms in a molecule. And bond length can be measured by spectroscopic or X-ray diffraction and electron diffraction techniques. So for each atom of the bonded pair contributes to the bond length as per the example diagram. This is the one we have to discuss. In the case of the covalent bond, the contribution from each atom is called the covalent radius of that atom. So the covalent radius is measured approximately as the radius of the atom is core which is contact with the core of an adjacent atom in a bonded situation, right? So bond length in a covalent molecule is there are two molecules, that is A and B molecule. Okay, here the radius R is equal to RA plus RB. What are those RA, RB? As the R is the bond length and RA and RB are the covalent radii of the atoms A and B molecules respectively. Okay, so the covalent radius is half of the distance. The covalent radius is half of the distance. So this is the covalent radius. This is half of the distance between the two similar atoms joined by a covalent bond in the same molecule. So the van der Waals radius represents the overall size of the atom, which includes its valence shell in a non-bonded structure. The van der Waals radius is half of the distance between the two similar atoms in separate molecules is a solid. A covalent and van der Waals radii of chlorine are, we can show like this. Yes, we can show like this covalent radius. This is like this. Okay. So this is the outer cover. Again it will comes more atoms. Okay, here from this to this is around 198 picometer. Okay, same way from this to this is approximately 180 picometer, and compared to this top to bottom it will give 360 picometer. Here The covalent radius we can represent it like this, RC. Covalent radius is RC. Okay, and van der Waals we can represent it RVDW. So this is indicates the van der Waals abbreviations. So this this is typical average bond lengths for the single, double and triple bonds are shown in the below table. There are O dash H bond having covalent bond length 96 picometer, O dash H. Then C dash H having 107, NO 136, C dash O is 143, and C double bond O is 121, and C double bond C is 120. Okay, and the bond lengths for some common molecules also we are given in this table. In this table we are given the common molecules which is having the same bond lengths, or with the H2 H dash having 74 bond length, that is picometer. So same you can see another few examples also is given. N double bond N, so it is having 109, right? Same way for O2 O double bond O is 121, hydrogen iodide is H dash I is 160 picometer. The covalent radius of the some common elements also listed in the in this table we have listed the some common elements. Some common elements we have listed in this table having the covalent radii. Say for example, for hydrogen, so 37 the covalent radii, carbon having 77, like this. So the values of the cited whatever is given are, except where the indicated parenthesis is different, that we discussed in the previous chapter, periodic trends. So this is about the bond length. Now what is the bond angle? So bond angle is defined as the angle between the orbitals containing bonding electron pair around the central atom in a molecule or complex ion. So bond angle is generally expressed in degree. Bond angle is expressed in degree. Okay. So this is which can be experimentally determined by spectroscopic method. So it gives some idea about the distribution of orbitals around the central atom in a molecule or complex ion. So hence it helps in the determination its shape. Say for example, water, H dash O dash H. Here the bond angle in water can be represented as, bond angle of the water can be represented like this: O, there are two unpaired valence electrons, and hydrogen dash hydrogen. This is the bond angle of water molecule here. So this is equals 109 104.5 degree. Okay, so now the third one is bond enthalpy. Bond enthalpy, bond enthalpy we can define as the amount of the energy which is required to break 1 mole of the bonds of the particular type the between the two atoms in a gaseous state. So bond length is the amount of the energy required to break the 1 mole of bonds of a particular type between the two atoms in a gaseous state. The unit for bond bond enthalpy is kilojoule per kilojoule per mole. Kilojoule per mole is the bond length. Okay. So for example, so hydrogen having the hydrogen H2 H dash H. So the bond length in this hydrogen molecule is the 435.8 kilojoule per mole. So bond length, bond enthalpy of hydrogen molecule is 435.8 kilojoule per mole. Same way, see, hydrogen H2 is a gas discussed. Then it will give again gas only. Then again it will give one more gas, that is H2. Here the delta A H minus is equal to 435.8 kilojoule per mole. Okay. So similarly, the bond enthalpy for a similar molecules which is containing having the multiple bonds, for example O2 and N2, we can say O2 is O double bond O, same way N2 is N triple bond O. Okay, for these two examples we will discuss how the what is the bond enthalpy. See, O2 as we given in the previous, O double bond O, this is gaseous state, so which is plus O, both are gaseous molecules. Okay, so here we'll get the enthalpy of hydrogen is delta A H minus is equal to 498 kilojoule per mole. Okay, so same for nitrogen, which is where having the N triple bond where the having triple bond. So this gives us, this is gaseous state, so it will gives nitrogen is one of the gas plus nitrogen is another one liberated. So here the enthalpy, degree of enthalpy is, so delta A H minus is equal to 946 kilojoule per mole. So it's very important that the larger the bond dissociation enthalpy, stronger will be the bond in the molecule. For a heterodiatomic molecules like HCl, say for example HCl, see HCl is in the form of gas. This liberates hydrogen plus chlorine. Okay, here bond enthalpy of the HCl is 431 kilojoule per mole. Okay, and in the case of polyatomic molecules, what will happen? In the case of polyatomic molecules, the measurement of the bond strength is more complicated than a single bond or double bond, where a single molecule or more than two molecules. See, in polyatomic molecules, for example water, here the bond enthalpy is needed to break the two molecules of O-H bonds are not the same. See, H2O in the form of gas liberates hydrogen, also gas plus hydrogen oxide. So here what will happen, there are 502 kilojoule per 502 kilojoule per mole. This is the enthalpy constant of water. Same way we can write this equation like this: OH, hydrogen, OH in the gas form. This gives hydrogen plus oxygen, which is having the enthalpy. Bond enthalpy is 427 kJ per mole. Okay. So here the difference in the bond enthalpy value, which shows that the second O-H bond undergoes some change because of the changed chemical environment. So this is the reason for some difference in energy of the same oxygen H bond is different in molecules like C2H5OH or ethanol and water. Therefore, in polyatomic molecules, the term mean or average bond enthalpy is considered or used. See, it is obtained by dividing the total bond dissociation enthalpy by the number of bonds between the explained, like the water molecules. See here, the water molecules having average bond enthalpy, you can find it as average bond enthalpy. So average bond enthalpy is 502. 502 is water plus 427 is OH. Divided by 2, we will get 464.5. 464.5 kilojoule per mole. This is the average bond enthalpy of water and hydrogen oxide. Next, the bond order. See the bond order. So this is finished. Now the bond order. In the Lewis, a description of the covalent bond, the bond order is given by the number of bonds between the two atoms in a molecule. Bond order is given by the number of two bonds between the two atoms in a molecule. The bond order, say for example H2 with a single shared electron pair, H2 having a single pair electron pair. Same for O2 having the two shared electron pairs, and in nitrogen having three shared electron pairs. So there are bond order is hydrogen is 1, oxygen O2 is 2, and nitrogen is 3. Similarly for carbon monoxide having 3 shared electron pairs between the carbon and oxygen. So the bond order for carbon monoxide is 3. For N2 bond order is also 3, and its delta A H minus. So enthalpy bond enthalpy is 946 kilojoule per mole. Okay, so this is being one of the highest for a diatomic molecule. In isoelectronic molecules and ions, they are having identical bond orders. For example, F2 and O2 2 minus have the bond order 1, okay, and nitrogen CO and NO plus having the bond order 3 bond orders. Carbon monoxide and nitrogen oxide is 3. Generally, the correlation is very useful for understanding the substitutes of molecules in that with increase in the bond order, and bond enthalpy increases and bond length will be decreases. So resonance structure. So resonance structure, we observed that a single Lewis structure is inadequate for the representation of the molecule in conformity with the experimentally determined parameters. Say for example, ozone having O3 molecule, ozone is O3, so which can be equally represented by the structures, as this is the structures. So this is equally, ozone is equally represented by the structures, sorry, yeah, this is the structure, resonance structure of the O3 molecule. In both the structure we have O dash O, O double bond O, okay, and a single bond and double bond. The normal O dash O and O double bond O bond lengths are O dash and O double bond O bond lengths are, so 148. O dash is 148 picometer, O double bond O is 121 picometer. Okay. Yes. Here uh, if you are taking the experimentally determine this resonance structure, in that oxygen to oxygen bond length in the O3 molecule are same. See here, both are having same 128 and 128 picometer. Thus, the oxygen dash oxygen bonds in O3 molecules are intermediate between the double and the single bond. So obviously this cannot be represented by either of the two Lewis structure shown as this is. Okay, here the Lewis structure is representing equally for this molecule and this molecule having 121 and 148 picometers. The concept of the resonance structure was introduced to deal with the type of the difficulties which is experienced in the depiction of the accurate structure of the molecules like ozone O3. According to the concept of the resonance, so whenever a single Lewis structure cannot describe the molecule accurately, a number of resonance structures with a similar energy or positions of the nuclei bonding and non-bonding with the similar pairs of the electrons are taken as the canonical structure of the hybrid, which describes the molecule accurately. Thus, for O3 ozone, the two structures shown above, these two are canonical structures of or resonance structures. So, and their hybrid is third one. These two hybrid is third one. Okay, the third structure represents the structure of ozone 3 more accurately. This is called the resonance hybrid. So resonance hybrid is represented by a double-headed arrow. Double-headed arrow resonance. Okay, so in generally, see, you can state resonance structure. Resonance stabilizes the molecules as the energy of the resonance hybrid is less than the energy of the any single canonical structure, and the resonance averages the bond characteristics as a whole. Thus, the energy of the O3 resonance hybrid is lower than either of the two canonical forms 1 and 2. So, many misconceptions are there with Lewis structure as well as resonance structure. This the canonical forms have the no real existence. The molecules does not exist for a certain fraction of time in one canonical form and for the other fractions of the time in other canonical forms. So there is no such equilibrium between the canonical forms as we have between the tautomeric forms ketone and enol in tautomerism. So the molecules in such as single structures which is in the resonance hybrid of the canonical forms and which cannot be as such depicted by the single Lewis structure. And with this, in this video we will going to be solve two more questions here. So how do you explain the structure of CO3 2 minus in terms of the resonance? Okay, how do you explain the structure of CO3 2 minus? CO3 2 minus. See here, the single Lewis structure based on the presence of the two single bonds and one double bond between the carbon and oxygen atoms is inadequate to represent the molecules accurately. So as it is represents unequal bonds, according to the experimental findings, all carbon to oxygen bonds in CO3 2 minus are equivalent. Therefore, so this carbonate ion is best described as a resonance hybrid of the canonical forms structure 1, 2, 3. So first structure is O double bond dash O dash O minus of either side. There are 2 valence electrons here, 6 are there. So another hydrogen atom having 6 valence electrons. Sorry for the disturbance. Okay, so another one structure, that is one structure. So another one structure which is having, there are 2 here, there are 6 valence electrons are there. O dash C, this is C double bond O dash O. Here there are 2 are there. So this is one second structure, and the third structure is O 6 dots dash C dash O double bond O. So this is the third canonical form of the carbonate ion. So second example we will take carbon dioxide. Explain the carbon dioxide structure molecule. Experimentally, the determined carbon to oxygen bond length is a CO2 is 115 picometer. CO2 is 115 picometer. Okay. The lengths of the normal carbon to oxygen bond double bond C double bond O and carbon to oxygen triple bond C triple bond O. C double bond O and C triple bond O are 121 is double bond is 121 and triple bond is 110 picometer. So the carbon to oxygen bond length is 115 picometer, that is average you have to take. So like the between the values of the carbon C double bond O and C triple bond, so obviously the single Lewis structure cannot depict the position, and it becomes necessary to write more than one more Lewis structures. So to consider the structure of CO2 in the best described in the hybrid resonance hybrid form of the canonical structures 1 and 2, 3. There are 3 canonical forms for carbon dioxide. See, one is O having all 8 O double bond dot C dot. Okay. Next O dot. This is first structure. Okay. The second one structure O dot. There are 8 valence electron C, next dot here O dash plus O minus. This is the second structure, and the third resonance hybrid structure is O plus dot dot C dot O dot dot. This is the third canonical forms of the carbon dioxide. I hope students this video is helpful to understand the chapter 4 bond parameters. Thanks for watching the video.